at the beginning of the Proterozoic wasn't that much different than life during the late Archean, right? So there was still a lot of single-celled prokaryotic organisms like cyanobacteria, and they constructed these algal mats that formed the stromatolites. However, there was also more advanced life during this time. These are what we call eukaryotes. Eukaryotes became more abundant during the middle of the Proterozoic, eventually dominating during the Neoproterozoic. And we know this from the fossil record. Eukaryotes, they contain a nucleus and they're larger and more complex than prokaryotic cells. Right? They can still be single-celled, but they're more complex. They have a nucleus. Now, evolution of the eukaryotes was a major process in Earth's history, in the history of life. And this is because they were able to sexually reproduce. Prokaryotes cannot sexually reproduce, right? Asexually, they just pass on their genetic material to their offspring. So they're basically clones of themselves. However, eukaryotes could sexually reproduce. So this was the first time that we had genetic material being shared between parents and passed on to the offspring. Right? And we know that in order to have evolution, you have to have that genetic material being mixed and passed down to the offspring. And this causes the genetic, the gene pool to change through time. And that causes evolution. So after eukaryotes evolved, evolution began to pick up. Now, again, Earth's early atmosphere and hydrosphere were largely devoid of free oxygen. This is because any of the oxygen that was produced in the atmosphere was very quickly taken down into oxygen-loving elements like iron, right? So as that oxygen went into the atmosphere, materials like banded iron formations quickly took that oxygen out of the atmosphere. However, as time went on and these banded iron formations and other oxygen-loving elements became overwhelmed, more and more oxygen was able to build up in the atmosphere. This could have been due to an increased bacteria photosynthetic activity, right? But whatever it was, as the atmospheric oxygen increased, so did oxygen in the ocean. As there was oxygen in the ocean, the nitrogen in the ocean was able to form nitrate, which is an important nutrient for eukaryotic algae. And this could help explain the expansion of eukaryotes during the Proterozoic. Now, as I said, because of eukaryotes, life could begin to more quickly evolve on Earth. Most of the ancient multicellular organisms are known from the Paleoproterozoic shallow marine rocks in Western Africa. We still have fossils of these back then. And most of them were multicellular metazoans. Metazoans are soft-bodied organisms, right? They don't really have a face, they don't have eyes, they don't have sensory organisms. You might not even realize that they're alive, but nevertheless, they were animals. And they were preserved as imprints, often in the mud. Now, the last period of the Neoproterozoic after the Cryogenian was the Ediacaran. The oldest Ediacaran fossils, again, they were preserved after snowball Earth. And as Earth warmed, there were more opportunities for the Ediacaran biota to move into new shallow marine, warmer regions, proliferate, evolve, and eventually become imprinted as fossils. Now, during this time, life, again, it was just soft-bodied, right? There were some small share-bearing fossils, but not a lot of hard body life, right? Not a lot of skeletons to be found or shells to be found.